Well, welcome to the fourth week of the course. This week we will be studying hypothesis testing for two population parameters. The parameters that we will test will be two population means and two population proportions. We will start off this week with testing two population means, where we will cover a z-test and then two different kinds of t-tests. So I have with me Professor Wan. So Professor Wan, why do we need to test two population parameters? What is the idea behind performing a hypothesis test, for example, in this case, for the difference between two population means?
The short answer is because we want to compare, if we have two data sets, we want to be able to compare the variability between the means of the two populations. So we want to see if within a certain given range, the mean values will be similar.
Correct. Okay. So essentially what we're doing here then is we have two populations and we are testing whether the means of those two populations are different, or in other words, significantly different or not. And when we talk about the concept of significantly different, we mean in terms of the statistical significance. And so we will use concepts from the previous week, where if you remember, we studied hypothesis testing for one population parameter, so where we tested the population mean or the population proportion. This week we're just extending those concepts to cover two populations, and this time we're just comparing the two populations. And we're not comparing the data for each population, we're comparing their statistics. And to be specific, we are testing the mean and the proportion. So let's start off with two sample z-test for population means. So recall we use the z-test when we know the population standard deviation. So this is the case where we know population standard deviation for the first population and the second population. And the hypothesis test will start off with the null and alternative hypotheses. The null is always one where we include the equal sign. So we will say that the mean for the first population equals mean for the second population. You can also rearrange it. Sometimes you'll see that this is written as mu1 minus mu2 equals 0, because you can bring this mu2 on the left side of the equation. So this becomes mu1 minus mu2, and then you are left with equals 0. That's also okay to display, and this is okay as well. The idea is that under the null hypothesis, we always assume that the two means for these populations are the same. The alternative can take three different types, and we studied this last week. One is where we have the less than sign, or the greater than sign, or the not equal sign. And in this case, in the case of two populations, we have that the mean of the first population is less than mean of the second population, or is greater than the second population, or it's not equal. So you'll be choosing one of these based on the problem statement. And then recall we studied the test statistic. This is the formula for test statistic. In this case, it involves statistics from both the samples. So since we are comparing the means for two populations and we're performing a hypothesis test, so clearly we will be collecting samples from each population. The first sample will give you the sample mean, and it will give you the sample size, which is what n1 is. The sigma 1 here, sigma 1 square, this is the standard deviation square. In this case, it's the population standard deviation that is going to be given to you. The second sample will again lead you to its own sample mean. its sample size, and the population standard deviation for the second population would be given to you. So you plug that in, that's your test statistic, and then the rest is the same. Calculating the p-value will be the same, comparing it to alpha will be the same, the rest of the steps are all the same. Here is an example from Zyvox. So a study is conducted to determine whether extrasensory perception is a real phenomena. 50 subjects claiming to have ESP answer a set of questions, testing the subject's abilities. 60 subjects who do not claim to have ESP also answer the question. The results of the tests are summarized below. So here are the results. So essentially you'll be looking at the mean score for ESP group is 12. The mean score for non-ESP group is 10. And here are the population standard deviations given for each group. Is there sufficient evidence supporting the claim that the mean test score of subjects claiming to have ESP is different from the mean test score of subjects who don't claim to have ESP? Alpha is given as 0.05. So again, we start off with the null hypothesis. The null hypothesis is that the population mean of ESP group is the same as population mean of the non-ESP group. And the alternative will set it as not equal because based on the problem statement, we're trying to see whether the mean score of ESP group is different than mean score of non-ESP group. The keyword here is different. Different can mean less or more, hence we pick the not equal sign here. Plugging in these values into the formula for z statistic, we get our z statistic as 2.44. And because we're considering a not equal alternative hypothesis, so we have to look at the tails of the z distribution, both the tails, not just one, because it's a not equal sign. So, and then we need the area to the right of 2.44 and area to the left of negative 2.44. When you combine these areas, you get the p-value as 0.015. And since this p-value is less than 0.05, we can reject the null hypothesis. And we can say that there is sufficient evidence that the mean score of subjects claiming to have ESP and those who do not are indeed statistically different. In Python, we can perform the same hypothesis test, the z test, and the way we do that is we define our two samples. So here are two samples that are given to us, and we can use the z-test method from statmodels.stats.weight_stats submodule, and the inputs to the z-test method are x1, which is the sample data for the first sample, and x2, which is sample data for the second sample. And when you run this, you will see that, again, just like last week, you'll get two numbers here. This is not the confidence interval. We're running a hypothesis test, and therefore we would expect that the first number will be the test statistic and the second number will be the two-tailed p-value. Now, based on your alternative hypothesis, if the alternative hypothesis is set to not equal, meaning we're considering two tails, then this is the p-value to use to compare to alpha. If, however, the alternative hypothesis is set to greater than or less than sign, then recall that we need to divide this by 2. And then once we divide it by 2, the new p-value that we get is the one that we compare with alpha. Now, Professor Wan, what is one of the issues here with these samples that we're considering?
Basically, it's a sample size. So you need to keep in mind that in the real world, if you're going to apply the center limit theorem, you need to have a sample of at least 30 if you're going to apply the z-test. Otherwise, we will have to use the t-test if it is less than 30. For all practical purposes, we will just follow the procedures in this case with a small sample to keep it simple.
Now, the second case is one where we use the t-test to compare the two population means. Recall that this is usually the case when we're not given the population standard deviation or your sample size happens to be too small. In general, if it's less than 30, it's recommended that you use the t-test. Or again, if you don't know the population standard deviation, which happens in a lot of instances, can't make any assumptions on what the population standard deviation is, that's when we should use the t-test. Now you'll notice here there are two types of t-tests given to us. So Professor Wan, what are these two types of t-tests? What is the difference between them?
Well, they're basically the pair t-test, also called the dependent t-test, and the unpaired t-test or the independent t-test. So let's look at the meaning. Let's follow the definition given as to why they're using dependent versus independent. So in the case of the paired t-test, we have a sample taken from one population but is exposed to two different treatments. For example, the main idea is that measurements are recorded from the same group, usually before and after a treatment, and is applied when each of the two treatments is applied. In the case of the unpaired t-test or independent t-test, a sample is taken from one population, however, it is not related to a different sample taken from another population. So comparing it to the paired t-test, measurements are taken from an unpaired t-test are recorded from different groups when exposed to the same treatment.
So here's the first test, the paired t-test. Just like Professor Wan said, in the paired test, also called the dependent test, a sample is taken from one population which is then exposed to two different treatments. So measurements are taken before and then after the treatment, and then the idea is to compare if there's a significant difference in the average, in the mean of those measurements. So if you notice here, this is the test statistic that's given. You'll notice that in a paired t-test, we have D bar. D represents the difference, and this is the difference in measurements prior to and post the treatment. SD again is the sample standard deviation of the differences. D bar is the mean difference between the samples, again prior and post, and then N is the sample size. And if we move on to the actual test, the null hypothesis is that the mean difference is equal to 0. So just like before, the null hypothesis always includes the equal sign. The alternative hypothesis could take three forms. The first is that the mu d is greater than 0. That's the right tail test. Mu d is less than 0. That's the left tail test. And mu d is not equal to 0, which is the two tail test. And again, the mu d is the mean difference between the population measurements prior and post. And again, this is our test statistic that we just covered. Recall that when we use the t-distribution, we always have the degrees of freedom. So the df equals n minus 1 in this case. And once we have our test statistic t, we calculate our p-value. And recall that all Python functions return two-sided p-values. So if you have a two-tailed alternative hypothesis, you will just use the p-value that's output in the Python method, compare to alpha to reach your conclusion. If you have a one-tailed alternative hypothesis, either the right or the left, then you will take that p-value output from Python method divided by 2 and then compare it to alpha to reach your conclusion. And the conclusion is the same as before. If the p-value is less than alpha, you reject the null hypothesis. If the p-value is greater than alpha, you do not reject the null hypothesis. And usually students will ask, if the p-value equals alpha, then you can reject the null hypothesis. So here is an example from Zybooks. Example 5.7.3. The caffeine dataset uses data from the effect of different dosages of caffeine on endurance performance time. International Journal of Sports Medicine is where the data is taken. It gives the endurance times in minutes of 9 athletes when given a caffeine dose of 5 milligrams and 13 milligrams. So it's the same athlete who's first given a dose of 5 milligrams and then given a dose of 13 milligrams, and their endurance time is measured. So here's the code for it. We're going to be using scipy.stats, where we have the t-test that we will be using. We'll use pandas to import data from caffeine dataset. So we import that into a data frame, and then the two columns that we're interested in are called mg5 for 5 milligram dosage, and then 13 dosage is mg13. We'll use t-test underscore rel method from scipy.stats submodule. That is what performs the pair t-test. So let's run this. So once you run this, you'll see that you'll get a test statistic and a p-value. Now the test statistic is negative 0.12 and the p-value is 0.90. Now we look at the unpaired t-test. So just recall Professor Wan mentioned that in an unpaired t-test, you're really comparing two different populations. The case is not where you have a post and prior treatment samples. You're comparing two different populations, hence you have two different population means as given here. This is your t-test, and hence this is the test statistic for the t-test. It equals x1 bar minus x2 bar minus mu1 minus mu2. Under the null hypothesis, this will be 0 divided by the variance for the first sample, s1 square over n, plus variance of the second sample, s2 square over n2. And so the rest of the steps are the same. You will start off with setting your null and alternative hypotheses. As it says here, the null hypothesis is always where mean of the first sample equals mean of the second sample. And recall that we're considering the population means here. The idea behind the null and alternative hypothesis is to make some kind of a claim about the unknown population mean. This is why we're using the mu's. The alternative hypothesis can take, again, 3 different types based on the problem statement. The first can be mu1 is greater than mu2, or mu1 is less than mu2, or mu1 is not equal to mu2. So you calculate your test statistic t, which is the mean for the first sample minus mean for the second sample, and then divided by this. All of this data will be sort of given to you when you have a sample. And don't forget, we will be calculating the degrees of freedom. Remember that last week we were considering the t-test. We had df equals n minus 1. That's because we only had one sample involved. Now, because we have 2 samples involved this week, our degrees of freedom will be n1 plus n2 minus 2. And again, you get your test statistic t, so you can get to your p-value based on that. And then once you have the p-value, depending on the form of the alternative hypothesis, whether it's one-sided or two-sided, you will either divide the p-value by 2 or not, and then that is the one that you will then compare with alpha and reach your conclusions. In this example, we are considering 2 packing machines. So to improve production capacity, a manufacturing company buys a new machine that claims to pack 50 widgets in a carton faster than the old machine can. So the idea is that we have now two samples, and these are independent samples because in the first sample we are considering the packing times for the old machine. In the second sample, we're considering the packing times for the new machines. These are two different machines. They're independent of each other. Therefore, this is not a paired t-test. This is an independent t-test. So let's do this example in Python and see how this works. So this time we will use t-test underscore ind method. This is the method to perform the independent t-test. This is again imported from scipy.stats submodule. Machines.csv is the file that contains data for this, for these two samples. So we import that into a data frame, and then we use the columns old and new to reference the two samples. The first input to the method t-test_ind is the sample data for the old machine, and the second input is the sample data for the new machine. So we run this and we get our test statistic, which is 3.397, and our p-value is 0.0032. Again, based on the alternative hypothesis, if we have a two-tailed test, meaning that the alternative hypothesis is set to not equal, we will take this value as is and compare it to alpha. If the alternative hypothesis is set to less than or greater than one of the two, then we will divide this by 2 and then compare that with alpha to reach our conclusion. Now we move on to section 5.8, which is about hypothesis test for the difference between two population proportions. So Professor Wan, we've already covered the hypothesis test for difference between two population means. We saw that the steps to carry out the hypothesis tests were pretty much the same as what we did last week, with the difference being that the null and the alternative hypothesis involve two population parameters as compared to one last week, and our test statistic is slightly different. So when we perform hypothesis tests for the two population proportions, can you walk us through some of these steps here for the hypothesis test?
Sure. The thing to keep in mind is that the process is going to be similar. In this case, for example, the null hypothesis will be represented by H sub 0, and the two proportions P1 and P2 represent the proportions for the two samples. Now, in the same fashion, the alternative hypothesis will be less than or greater than or not equal. And keeping in mind, like Professor Kadri said, that the Python results are shown for a two-tailed test. So in this case, if you're calculating less than or greater than, then you would have to divide it by 2. Secondly, then we will then use the statistical software, in this case Python, to calculate the value for the z statistics. As the formula shows, it will take the difference between the two average samples, and keeping in mind that the 0 in this case represents the standardized normal distribution, the value for the mean, and this is y is equal to 0, divided by the average p-value times the opposite of that, what average is. That is why you see 1 minus p hat, because if the p-value is a given factor, then the opposite, to bring it to 100%, it will be 1 minus p times the sum of the 1 divided by the sample size, n1 and n2. And then we can go from there, once we have the z statistics, we can determine the probability value, which we will then compare to the alpha value, applying the same rules. If it is less than 0.05, we will reject the null hypothesis. If it's greater, we will retain the null hypothesis.
So the z statistic in this case is equal to p1 hat minus p2 hat. And what that means is these are the sample proportions. This is the sample proportion for the first sample, sample proportion for the second sample, divided by p hat. This is the overall proportion. So we will see in an example next how this is calculated, times 1 minus p hat, and multiplied by 1 over n plus 1 over n2. And again, this is your z test statistic, and once you get your test statistic, you can get to your p-value. And then just like Professor Wan said, depending on how your alternative hypothesis is set, you will either divide that p-value by 2 or not, and then finally you will compare that to your significance level alpha and get to your conclusion. So let's do an example on this and see how this works. We will consider example 5.8.1. So the campaign team of a candidate running for statewide office is concerned about candidates' appeal to both genders. A recent survey of voting adults found that if elections were held that day, 70 of 132 men and 63 of 105 women would vote for the candidate. So you can see that these are the proportions given to you: 70 out of 132 men, 63 out of 105 women. So you can calculate your sample proportions from this. The question is, does sufficient evidence exist that suggest that the percentages of men and women who would vote for the candidate are different at alpha 0.05? We set our null hypothesis and the alternative hypothesis. The keyword here is different, hence our alternative hypothesis is set as not equal. P1 is proportion of men who would vote for the candidate. P2 is the proportion of women who would vote for the candidate. And recall that these are not sample proportions given in the null and the alternative hypothesis. Recall that they always reference the population proportions or the population for any parameter under the null and alternative hypothesis is based on the population. That is the claim. Then we get our sample data together and we calculate our P1 hat. The hat sign here essentially means that it's a sample proportion, and P2 hat, which is the sample proportion for the second sample. So we calculate those, and these are the proportions. Then we calculate the overall proportion, which is people who would vote for the candidate, men and women, and then the total number of people in the survey. So we get that proportion. And then the test statistic is calculated just like I showed you earlier. We get negative 1.079. And because the alternative hypothesis is set as not equal, we can calculate our p-value and get to the conclusion. Let's now do the same example in Python. So in Python, we will be using the method called proportions_z test that is imported from the submodule stats models.stats.proportion. This method takes two inputs. The first input is a list of counts, and the second input is a list of total sample sizes. So just like what we saw, we had 70 out of 132 was the first proportion, and 63 out of 105 was the second proportion. So we will use 70 and 63 in the first list called counts, and the total sample size is 132 and 105 in the second list called n. And it is critical to make sure that the first entry in the list here, 70, corresponds to the first entry in the second list as 132, because this method then calculates the proportion itself. So it'll take this first number, it'll divide it by the first number in this list, and it will calculate the proportion that way. So if I had 105 as the first entry here and 132 as the second entry, then it would calculate the wrong proportions and therefore you would get the wrong results. So just make sure that this is set properly. So we will run this, and as always we get our test statistic and the p-value. The test statistic is negative 1.07 and the p-value is 0.28. And let's say that our alternative hypothesis is set as one-tailed test, so either it is less than or greater than. Then we will take this two-tailed p-value divided by 2, and then that is the p-value that we will compare with alpha. If alpha is 0.05, then that is what we will compare with 0.05 to reach our conclusion. And the rule is very simple. If the p-value is less than alpha, you reject the null hypothesis. If the p-value is greater than alpha, you do not reject the null hypothesis. Now we move on to the discussion for the week, and the discussion involves hypothesis tests for the difference between two population parameters. And the parameter that we're testing here are proportions. So this week you will be working with the same problem that you worked on last week, where we had studied about a manufacturing process at a factory that produces ball bearings for automotive manufacturers. And the factory wanted to estimate the average diameter of a particular type of ball bearing to ensure that it was manufactured to factory's specifications. Now the idea this week is that the factory has begun a new production line that is more efficient than the existing production line. However, the factory still needs ball bearings to meet the same specifications. To compare the accuracy of the new process against the existing process, the factory decides to take two random samples of ball bearings. The first sample is of 50, the second is of 75. For each sample, the diameter of ball bearings are measured. The idea this week is that you will have two samples. The samples will be unique to you. So again, your answers will be unique. So different students will get different answers, and that's perfectly fine. So you may reach different conclusions based on your analysis. Now suppose that the factory claims that the proportion of ball bearings with diameter values less than 2.2 in the existing manufacturing process is the same as the proportion in the new process. So the proportion is defined as diameter less than 2.2 divided by all diameter that are in the sample. The alpha is set as 0.05, and we have to perform the hypothesis test. Here we have some of the questions that are involved for the initial post and then the follow-up post.
Very similar to the problem that we just reviewed. So let's look at the first step. You need to write in a statistical format the null hypothesis, that is H sub 0, and the alternative hypothesis. And in this case, the null hypothesis is that the p hat for process 1 will be equal to the p hat for process 2, because we're saying that the two processes are the same. On the other hand, the alternative hypothesis is that they are not the same, which in this case is the not equal sign. And if we write those hypotheses, we comply with step number 1. The level of significance is given to us as alpha equals to 0.05. So we just know now what level of significance we're using for the test. Now we need to calculate the test statistic and the p-value, and this is the same formula that we applied before using the z-test, and we know that the sample size is sufficiently large for these two samples. Finally, we need to provide a conclusion and an interpretation based on the value that we find, and the interpretation for the p-test is dependent upon whether it's less than the alpha value or greater than. If it is greater than, we retain the null hypothesis, otherwise we reject it.
You'll see that in this week's Python code for the discussion, you have step 1, which generates your sample data. So it will generate the sample data for the 2 samples for you. And again, the sample data will be unique to you. So my suggestion is to just run this once and then leave it as is. So here we run this, and you can see that this prints just the first few observations of the 2 samples. Then we move on to step 2. We perform the hypothesis test for population proportions in this step. So you'll see that I'm doing some calculations here to get the counts of ball bearings where the diameter is less than 2.2. This is the second sample where the count is again the number of ball bearings with diameter less than 2.2. We put that into a list called counts, and then we calculate the number of observations in the first and then the second sample, N1 and 2. We put that in a list called N, and then we use proportions z-test with the inputs counts and N, the 2 lists that we created here, and we get our test statistic and the p-value. So let's run this. You'll see that this is the test statistic, this is the 2-tailed p-value. Just like Professor Wan said, we had set our alternative hypothesis for 2-tailed. So we will use this p-value, we will not divide it by 2, and we will compare this with alpha 0.05. Clearly this is much greater than alpha 0.05, hence we will be unable to reject the null hypothesis. And once you have gotten your calculations, and after answering these questions for the initial post, you will then answer these 2 follow-up post questions. How does your conclusion compare to other students? So just comment on the conclusions that other students reach, and in some cases maybe their conclusions will be different than yours, so just be on the lookout for that. And then, do they have the correct conclusion based on their p-value and the level of significance?